Hello to all my fans and friends and viewers, whoever's watching. Welcome to another statics lesson. Today we'll be talking about internal forces along with the moment of inertia. This will likely be a two-part video since it might take a while to cover both topics. So this first part will be on internal forces, and then I'll probably link part two in the description for moment of inertia. So when talking about statically internal forces, the main three types that you usually get into are shear forces, normal forces, and then bending moments. And I have a little diagram right here. The V represents the shear force, the M represents the bending moment, and N represents the normal force. And down here, I kind of explain each one a little bit more. So the shear force is the force that is applied perpendicular to the surface of a beam or any object in general. So this is just the shear force right here. And then here's kind of an example of what it technically does. It causes a given beam to push two parts of, or a given surface to be pushed in opposite directions. So like, I mean, like obviously you're never going to see a beam like this, but these are what the forces exerted on the inside are doing to it. And then we have the normal force, which is also called the axial force. Now, in statics, this isn't commonly used because most of the forces are being applied vertically onto, or most of the forces or loads are vertically applied, which causes there to usually not be any axial or normal force. So this is one that generally isn't talked about in an intro statics class, but it's good to know just in case it ever it ever is needed because it definitely still could be used, so it needs to be accounted for. And then we have bending moment, which, as the name implies, causes a beam to bend. So it's the internal of like the official definition is it's the internal moment that causes an object to bend. And the direction for this moment, the best way to think about it is when a beam, like when the moment causes a beam to be concaved up, it is positive, and when the beam is concave down, there's a negative bending moment. So here's another diagram. So this will be a positive bending moment right here because this is the left side of a beam, and if you think about how it would rotate or bend, this would cause it to bend upward, concave up. So this makes it positive. And given shear and bending, shear forces and bending moments, a common thing that is done is making a shear and bending diagram for these, which kind of is a big step since we haven't done a calculation with these yet, but you'll see how they all kind of tie into each other. So an important thing to note with these is that there is a very important relationship between shear forces and bending moments, which is that essentially the best way to think about it is that, so like if you go to the diagrams right here, the area underneath a shear diagram is what you base the moment curve on. So like right here, dm dx is equal to the shear force. And the reason behind this is that if you think about how a moment is calculated, let me draw on the board for a second here. So a moment is calculated by a force times a distance. So when you have external vertical loads like this, so like this is causing a moment right here. And that moment is essentially variant on the distance of how long a given cut of a beam is. So this is like an internal, like we're measuring the internal forces here. So we have our bending moment right here, and this bending moment will change based on the length of this right here. So for example, so like for the bending or for the shear force here, this length right here is essentially like your x value. And the further along you go on the x, your moment increases. So Let me scroll down. There we go. So as you go along the x, the magnitude of your moment increases, which makes sense because moment is proportional to the distance from a given point. So that's kind of the best way to think about it. I'll delve further into it on the example below, but that that's kind of just the best way to think of it when starting off with this. So a couple of things to note when doing shear and bending diagrams is that you want to recognize that the magnitude will jump based off forces and moments at a given point. So right here, you can kind of see a jump here, a drop here caused by this, and then a jump back up, which we'll also get into in the example. It's kind of tough to visualize all this until you get into example, but these are important points to note. And then so applied loads, which are essentially loads that um that are that go along a given distance. Let me just draw it out real quick. So like this right here. So like this is an applied load, so it can be like 4 newtons per meters over like 2 meters or something. And when you run into one of these, you want to think about it like point loads on either side when making cuts, because you have to make cuts in between each shear moment or shear force or bending moment, which I didn't mention earlier, but that's very important. You can kind of see it here. They make a cut there and a cut here. So when you have one of these, when you have an applied load, you want to make a cut like in the middle, essentially. You'll also be able to see that in the example. And then a really important thing to note is that for these graphs, the values will always come back to 0, which if you think about it makes sense because there are no internal forces outside of the beam. And by the time you get to the length of the beam, you're essentially like out of it at that point. So all the values always have to end at 0. That's a good way to check your work, make sure it's right. Definitely is very, very helpful. So now we're going to get into an example problem. So this one, we're going to draw a shear and bending moment diagram for this beam right here, along with solving for these unknown reaction forces, which is pretty simple as long as you have a basic understanding of statics. So we use our equilibrium equations. So here are my shear and bending diagrams. Might be a little confusing to look at right now, but it's actually very, very easy to find. So I'm just going to go step by step. So you want to look at it by each point load, and then obviously the applied load we want to give special consideration for. So starting at x equals 0, you can see that there is a reaction AY going up, which causes there to be a shear force of 12 newtons. So I actually solved it right here just so you could get an example, but as you do more of these, you kind of are able to do them pretty quickly mentally, and you're able to kind of just draw these out with relative ease. So like you can see, V in the positive direction is actually going down. So when you draw these, that's a very important thing to note. So that, as I mentioned earlier, just causes a jump up to 12, and then it remains constant until you run into the next load, which is this applied load. So up until this point, it just stays at 12. And as you can see for the moment diagram, it is just a constant slope increasing up until 12 because this there are no other forces for 1 meter. And if you go here, this relationship is actually AY times the length X, and the furthest this relationship is true is up until this applied load. And then that max distance is 1 meter. So it's just a linear relationship. This line you can think of as 12x and caps off at 12. So then we have our applied load, which is where things get a lot more interesting. From here to here, from the start until this extra 6 Newton force going downward, the shear force varies based on the distance. So the magnitude of this changes based on where you make the cut. So for example, if you make this cut like right here, so let's just say this distance is like 0.5 meters. kind of tough to write it out on a trackpad, but 0.5 meters, and this applied load is 4 newtons per meters. It's only a force of 2 newtons, and this will keep changing based on where you make the cut. So um, this relationship with the shear force is actually also dependent on the length. So it's a linear decrease from here since this force is going downward. So up from here to here, it drops from 12 to 8 because it is 1 meter until this next force going down. So 1 times 4 is 4. So 12 minus 4, you go down to 8. And then an interesting to note here with the moment diagram. So as we mentioned earlier, the relationship between the two, that you can essentially think of the moment as like the integral of v dx. So it actually is a parabolic relationship. Since this is linear, this is parabolic. Kind of similar to how this is constant, and then that makes this a straight line because the integral of like a constant number is just the constant times x, and then integral of x is x squared over 2, and like so on and so forth. So you can actually kind of see that here with, so I did an example of how you would solve like the quantitatively this moment. So we have 12x right here, which is just the initial AY applied load, and then x is the distance from wherever you make the cut. And then you actually have 4 times x minus 1. So what this is right here is you have to subtract this distance by 1 because so x represents the entire distance from the cut, and that will be greater than 1 because we have this applied load that we need to account for. And you need to take off 1 because it is essentially just this distance minus whatever distance we have here, which we know to be 1 because it's given. So that's kind of the best way to explain it. So this is just x minus 1, and that goes into the magnitude for the applied load. But the interesting part is the distance from the cut, which is where we're taking our moment from. That's usually where you tend to take the moment from. And that would actually be this x minus 1 divided by 2, since we usually consider the point load of an applied, like these applied forces, to be in the middle. So it's just essentially half this distance. So this is the relationship you wind up having for this moment equation. So that's essentially what this graph is building off of. So like it is just a parabola essentially, and you, to find this value, the maximum at the end of each like kind of interval, if you want to call it that, you just plug in 2 here and you get 22. So I know that this is going to be at 22. So now when you go through the other ones, you actually have another dip of 6 newtons, which brings this from 8 to 2. 8 minus 6 is 2. And then you continue this decreasing slope because this applied load has not ended yet. So it keeps going until it ends. Now, an interesting thing to note, very, very important, is that now we are under the curve and the shear force is negative. So that means that the moment will now decrease, since when you take the integral under and the area is under a curve, it will be negative. So now this moment now the moment will decrease as a result of the shear being negative, since it's essentially the area underneath this curve. And we calculate it to max out at 22.5 because we know, kind of complicated, but I'll try to get through it quickly, that it's at 0 here, which when a derivative is 0, that can be like a local maximum. So that's how we know that this is like the max here. So it's just essentially, I actually solved it, right? I solved for the extra area right here. This will be another point I get to, but it's essentially just 22 plus this little area right here, which is just 0.5. So it increases to 0.5. And you kind of just continue solving for these areas in order to get all of these regions. This is the quicker way to do it. I just wanted to show the more quantifiable way, like the conceptual way behind it, because it's important to understand this before you just make these calculations. So yeah, you can just solve for all these areas under the curve that you get, and I'll just go through the rest of these so you can see where they come from. So this stays constant because remains constant after this applied load ends because there's no other forces being acted upon it. And then there's a decrease of 7 newtons going down, so it drops from -2 to -9. Then it goes back up from -9 to 0 because BY we found to be 9 newtons. So this ends at 0 newtons, which is good. That means that hopefully it's right because it has to end at 0, as I said earlier. And then from here, you're able to take all the areas underneath these curves just using basic geometric methods. So these earlier ones, these confirm my the moments I calculated before. So this area is 12, or this will go up to 12 because this area is 12 right here, up another 10 to 22, up 0.5 from this little triangle right here, A3, then down another 0.5, and then down 4 because this rectangle is -2 by or 2 by 2. So it goes down 4 and then down another 18. This is supposed to be a negative sign right here. -18 right here because there's this large area right here. It's 9 by 2. And that brings it from 18 down to 0. So these both end at 0. That means that they're probably statically correct. And this is just one example. Definitely practice more of these. You're probably not going to understand it from this. You can just review this video when you're solving your own problems. And yeah, so that'll be part 1. That concludes part 1 of the video. Part 2 will be in the description, and that will be solving for the moment of inertia.